To understand quantum error correction, a good starting point can be classical error correction, and in particular classical 3-bit repetition code. So today we will try to understand what is a repetition code, like a classical repetition code, and then using the same principles we will try to understand quantum 3 qubit repetition code. I mean, we will figure out that quantum 3 qubit repetition code does not serve the purpose of protecting the quantum information completely, but at least the basic idea of quantum error correction you can get from here. And in future sessions, I will try to discuss more interesting codes. So let's today try to get a high level essence of quantum error correction through repetition code. So its simplest starting point for understanding quantum error correction is classical 3-bit repetition code. So as we say it's a repetition code, like as we know it because it's a repetition code, it encodes bits by repeating them because it's a repetition code. So for example, let's say you have to encode 0, then 0 is encoded as repeating 0 few number of times. So let's say I repeat it 3 times, then 0 is encoded as 000, and you call this encoding of 0 as 0 logical, or the code word for 0. Similarly, the logical 1 is 111. So that's the code word for 1 basically here. Once you have done encoding, you have to see how it protects against errors. So what is an error that can happen in classical error correction? Now notice that we are only working with bits. So bits can flip. So that's the error that can happen in error correction, the classical error correction case. So the bit flip error is the error where bits flip. So you have 0, 0 flips to 1, 1 can flip to 0. So this is a bit flip error. So we had this encoding where 0 was encoded as 000 and 1 was encoded as 111. Now let's say that first bit flips. So let's say the first bit flip. So in that case 000 becomes 100. 111 becomes 011. Suppose the second bit flips. In that case, your code word, which is 000, will become 010 because the second bit has flipped. The second bit, it has flipped. So 0 has become 1. 111 becomes 101 because the second bit has flipped. Similarly, if let's say the last bit flips, then 000 will become 001 and 111 will become 110 because the last bit has flipped. Notice that whenever the bits flip, let's say if it's a single bit flip error, then the bits in the bit string, like in your string, the bits are no more identical. Earlier, like when you encode them, in a repetition code, the bits are identical. Here, after a single bit flip error, they are not identical. So when they are not identical, you detect that some error has occurred. So this is what you mean by error detection here. You look at the bit strings are not all identical, hence there is an error. So you detect an error. So this is error detection, and the process is very simple. You look at the bit string, if they are not identical, then there is error. How do you error correct? Okay, so you have detected error. You know that some error is there because bit strings are not identical. So let's say you had started with 0 0 0 and this bit flipped, sorry, just a moment. Okay. Okay, so you had started with 0 0 0 and this bit flipped, and in that case your 0 0 0 became 1 0 0. Okay. If the second bit had flipped, then it would have become 0 1 0. If the third bit had flipped, it had become 0 0 1. But you notice that the majority of the bits, they are still 0 in all these three cases. So what you do is that you error correct by resetting all bits to majority value. So if it's 0 1 0, you reset it to 0 0 0. If it's 1 0 1, then you reset it to 1 1 1. Now at this point somebody can ask a question that, let's say, we had started with 0 0 0 and let's say 2 bits flip. So let's say I get 1 1 0. In this case, if you reset bit to majority value, you will get 1 1 1. So in this case, if you reset it to majority value, you will get 1 1 1 and you don't recover 0 0 0. So setting bits to majority value does not work here. Why is this the case? The answer is given by code distance. I mean, we will see that it's code distance that tells us how many bits can flip and still you can do error correction. So code distance in classical error correction is defined as smallest number of bit flips required to transform any two code words into one another. So what are the code words for us? Our code words are 0 0 0 and 1 1 1. What is the smallest number of bit flip required to transform 0 0 0 to 1 1 1? It's 3. It's 3 here. So code for a 3-bit repetition code, the distance is 3. For similarly, if you have n-bit repetition code, then you have n zeros here and n ones here, and the number of bit flips required to transform this to this is basically n. So for n-bit repetition code, the distance is n. Okay. Now you can actually calculate, think of a scenario where there are many code words, and if you look at the definition, it says a smallest number of bit flips required to transform any two code words into one another. So you have to look at all possible code words, and then you have to find the smallest number of bit flips required to transform any code word, let's say A, into a code word B. So you have to look for the smallest number of bit flips required. So the object that helps you properly take care of it is this thing called Hamming distance. So Hamming distance, you can notice the definition is similar to what we see for the distance. It's the minimum number of bit flips to transform bit string A to bit string B. So you have one bit string and you have another bit string, and you ask for minimum number of bit flips to transform A to B. So for example, a Hamming distance between, let's say if you take A equal to 0 0 0 and B equal to 1 1 1, the Hamming distance between A and B here is 3. And what you do is that you calculate Hamming distance between all pair of code words, and then you take the minimum, and that minimum is your distance. So you look for all possible Hamming distances between different code words, and you take the minimum of that, and that minimum is what you call code distance. So it's smallest number of bits will required to transform any two code words into one another. So this part we have to like keep in mind, any two code words into one another. Yeah. So there can be many code words, and we have to find the minimum number of bit flips required to transform any two code word into one another. So code distance basically determines, it tells you the maximum number of errors which can be detected. So for example, if the distance is 3, then the maximum number of errors that can be detected is 2. And you can see that in the case of repetition code, this makes sense, because if let's say 2 bits flip, then still all the bits in the bit string are not identical and error detection will work. Similarly, code distance determines the maximum number of errors that can be corrected. So this relates back to like the question that we were asking, is that what if 2 bits flip here and then the resetting all bits to majority value does not work. By the way, here it should be ceiling, actually floor. So for d equal to 3, this number is actually 3 minus 1 by 2, floor of that, which is 1. So the maximum number of errors that can be corrected for distance 3 repetition code is 1. And because here we were talking about we were talking about 2-bit flip error, 3-bit repetition code did not work because distance was 3, and hence it can only tolerate it can only help you correct bit flip, single bit flip error. If there's a 2-bit flip error, then obviously it won't work. Nice. So we looked at 3 things. We had this n, which is number of bits in the code word. We had k, which is number of encoded bits, and we have d, which is code distance. And this nkd, you denote it as like in this form, like n11n. So this is for n-bit repetition code. So for example, if you are working with like let's say 3-bit repetition code, you denote it as 313. So n is equal to 3, k is equal to 1, and d is equal to 3 for 3-bit repetition code. Very nice. So you have encoded your information. You can also now detect error, you can correct error, but that's not all. You want to do operation on your encoded information, and for that what we mean is that logical operation on the code word. So basically the goal is to perform computation on the encoded information. So for example, you want to, let's say, transform, let's say you want to change 0 to 1. At the logical level, it means you want to change 0 to 1 1 1. And this operation is done by NOT gate. A logical NOT gate will basically take 0 0 0 and transform it into 1 1 1, and it will take 1 1 1 and transform it into 0 0 0. Okay, so that's what logical operation on the code means. So this gives you now a rough idea of classical 3-bit repetition code. Now using these insights, now we will try to understand quantum error correction by looking at quantum 3-qubit repetition code. So now let's look at quantum 3-qubit repetition code. Now here 0 logical is 0 0 0, 1 logical is 1 1 1, and because we are working now in the quantum case, we have to use this ket notation. Okay, so any quantum state which is, let's say, so in the quantum case, your quantum states, let's say, can be superposition of 0 and 1. So it's alpha 0 plus beta 1. So its encoding is very simple. It just becomes alpha 0 0 0 plus beta 1 1 1, because you just encode 0 as 0 0 0, 1 as 1 1 1. So alpha 0 plus beta 1 is alpha 0 0 0 plus beta 1 1 1. So your code space is a span of 0 logical plus 1 logical. That's what your code space is. And it can be thought of as error-free encoding of a quantum state, basically. So error-free encoding of a quantum state lies in this subspace. So you have a big Hilbert space, and there is a subspace, small space, where your error-free encoding of a quantum state lives. And whenever there is an error takes you outside this subspace. And then the job of error correction is to bring that quantum state back to the code space. So that's what we do in quantum error correction. Okay, so we have understood the code words. Now let's look at the errors. So earlier we had bit flip error. So your 0 can become 1, 1 can become 0. Now 0 qubit can become 1 and state 1 can become 0. But you have also in the quantum case this phase flip error, which we did not have in the classical case. So it's like the phase flip error is given by this Z operator. The Z0 is 0, Z1 is -1. So basically what it means that under bit flip error, alpha 0 plus beta 1 will become what? Alpha 1 plus beta 0. On the other hand, under phase flip error, so let's say if this is under bit flip error, under phase flip error, it will become alpha 0 minus beta 1. So here you have bit flip, like 0 became 1, 1 became 0, and here there is a phase flip. This phase has plus has become minus. So you have two kinds of error. You have bit flip error and you have phase flip error. Now there is this remark that I will prove in future sessions, but you can trust me, it basically says that if both X and Z errors can be corrected, more general errors can be corrected as well. So if you can correct X, if you can correct Z, then life is all good. You can correct more general errors as well. So earlier we looked at what were the code words, what was the error, and then we looked at what was the state, or let's say the bit string in the classical case after some error occurred. So similarly here looked at what is the encoded state after a single bit flip error, for example. So let's say you had alpha 0 0 0 plus beta 1 1 1, and let's say there is a bit flip happening on the second qubit. So it's like there is an action of this operator identity tensor X tensor identity. This is because bit flip error is given by this action of this operator X. So your quantum state will basically become alpha 0 1 0. So this 0 will flip to 1 and beta 1 0 1. So that's what the encoded state is after a single bit flip error. Similarly, you can calculate what happens to the encoded state after a single phase flip error, for example. Okay. So now let's look at error detection. So earlier in the classical case, we just look at the bit string. We look at it and we saw that if the bits are not all identical, then some error has occurred. But here there is a problem. You cannot measure individual qubits in the computational basis, because definitely you can measure and it would detect the error, but it would also result in the collapse of the encoded qubit. So this is a problem in the quantum case. But that does not stop us from doing quantum error correction. Instead of measuring individual qubits, what you do is that you measure symmetries of the state rather than individual qubits. You measure symmetries of the state. So for example, you can measure parity. So for example, the state 0 0, let's say 0 0 and 1 1, these strings have parity even. 0 1 and 1 0, they have parity odd. And you can use such circuits to measure parity. So this circuit, for example, here you have, let's say, some information, and you can start with some auxiliary resistor, and you can measure your parity by doing measurement on this auxiliary resistor and a bunch of control nodes. This circuit this is quantum circuit. It is equivalent to measuring Z tensor Z on first two qubits. So you notice that there is something interesting. 0 0 and 1 1 has even parity. 0 1 and 1 0, they have odd parity. You notice that Z tensor Z does not give any like sign in front if it has, let's say, if it has even parity. On the other hand, when it acts on 0 1 and 1 0, you get minus here. So Z tensor Z can help you figure out whether some bit flip error has occurred on your quantum state or not. So let's say the bit flip occurs on the first qubit. Then in that case, when you measure ZZ, you will get -1, because this register has the bit has flipped, and this one also you will get -1, because this Z is common, like like this is on the first qubit. On the other hand, identity tensor Z tensor Z, that will give you +1 and not -1. Actually, there is a very intuitive way to see it. Whenever error commutes with these operators here, then you get like +1, and when it does not commute, you get -1. So you look at this pattern of +1 and -1, and that helps you figure out which qubit has flipped. So for example, let's say your first qubit had flipped, then it would become 1 0 0, alpha 1 0 0 plus beta 0 1 1. Now let's say when you measure parity of the first two qubits, it's odd parity. So it's odd parity, so it's giving you -1. If you do these two qubits, again it's odd parity, so it's giving you -1. On the other hand, the last two qubits, they have even parity, so it gives you +1. And then by looking at this +1 and -1, you can figure out that, oh, it's happening because these two don't commute with xii, and that's why I am getting here -1 and +1 here. On the other hand, let's say you get here -1 +1 -1, then you know that the error is bit flip error on the second qubit. If you get +1 -1 -1, then you know that the bit flip error has occurred on the third qubit. So by just measuring this Z tensor I, and then Z tensor I tensor Z, so basically Z1 Z2 and then Z1 Z3 and then Z2 Z3, by measuring them you can figure out which qubit has gone through error. And through this way you actually do not collapse your state, and still you are able to extract information about which qubit has gone through error. So you measure symmetries instead of like measuring them in the computational basis. Very nice. So that's how you do error detection here. For error correction, it's very simple. So let's say you figure out that this error has occurred, the error xii has occurred. So you do nothing, you just apply the inverse of the error operator to correct the error. So if the error is xii, the correction operator is xii. And the idea is, why? One can ask why should we do this? Because polys are self-inverse. So xii and times xii, that is basically identity. So that does the job. So similar to the classical case, now one would say, okay, you did error detection, you did error correction, all of these things. You have some encoded information. On the encoded information, you need to do some logical operation, and logical operation should mimic the operation that you do on, let's say, unencoded case. So let's say we want x var and z var which behaves like x and z. So x basically takes 0 to 1 and 1 to 0. So x var should take 0 logical to 1 logical and 1 logical to 0 logical. And similarly, because z takes 0 to 0 and 1 to -1, z var should take 0 logical to 0 logical and 1 logical to -1 logical. So one possible choice of such x var is xxx and z var is zii. So for example, like let's say we had the state alpha 0 0 0 plus beta 1 1 1. This, because this mimic alpha 0 plus beta 1, and let's say if you had applied on this particular quantum state x gate, it would become alpha 1 plus beta 0. To mimic this, you want alpha 0 0 plus beta 1 1 to be transformed as alpha 1 1 1 plus beta 0 0 0. And this you can do by applying xxx. So if you apply xxx, you can go from alpha 0 0 0 plus beta 1 1 1 into alpha 1 1 1 plus beta 0 0 0. And for phase, for this z gate, you just apply zii. So it will change your plus to minus here. That's it. Actually, there are many such choices of operators that you can get, and how to figure out this logical operator, how to figure out. Actually, one can use some group theoretic idea, in particular this thing called stabilizer formalism, which we will discuss in the next session. One more thing remains, and that we will cover now. So this is basically distance of a quantum code. So we looked at distance of a classical code. Similar to that, we need to talk about distance of a quantum code. So to understand distance of a quantum code, let's first understand weight of any operator. So weight of an operator is number of qubit it acts non-trivially. So for example, if you have xii, it acts non-trivially on 1 qubit. ixi, again 1 qubit. xxi, it acts non-trivially on 2 qubits. zii, it acts non-trivially on 1 qubit. zzz, it acts non-trivially on all 3 qubits. Okay. And the distance of a quantum code is minimal weight of any non-identity encoded logical operator on the code. So you look at all possible logical operators which are possible, and among them you look at the minimal weight operator. So weight of the minimum weight operator, logical operator, gives you distance of a quantum code. So minimal weight operator of encoded x is 3, because your x was xxx, and this is the only possible logical x that's possible. On the other hand, for z, we have many possibilities: zii, izi, iz. Anyway, there are other possibility also, but you see that the weight of zii is already 1, and that's the smallest weight that you can get, because for distance we want non-identity encoded logical operator. So basically z is equal, for z case the distance is 1, for x case the distance is 3. So one can say that the x distance of the code is 3, the z distance of the code is 1. Actually, distance is taken as minimum of the x and z distances. So effectively, this code has distance 1, but still you can think of, like for x it has distance 3 and for z it has distance 1. So this code can detect, the quantum 3-qubit repetition code can detect 2x errors and no z errors, because 3 minus 1, like you see that, right? D minus 1, many errors you can detect, and d minus 1 by 2 errors you can correct. So here, because d is 3 for the x case, our d minus 1 is 2 and d minus 1 by 2 is 1. So the quantum 3 qubit repetition code can detect 2x errors, but it cannot detect any z error, because if, let's say, for the z case the distance is 1, and if you do d minus 1 you get 0. So it cannot detect any z error. Okay, so that's it. I mean, today we looked at some of the basic things here about classical and quantum error correction. So we started with classical 3-bit repetition code, and we looked at the code words, we looked at the bit flip error, the code word after single bit flip error, error detection, error correction, the notion of code distance, and also this Hamming distance, how it helps you understand code distance, this NKD notation, and the code distance basically help you determine the maximum number of errors which can be detected and the maximum number of errors that can be corrected. And then we looked at also the logical operation on the code. After that we switched to the quantum case and we looked at code words, errors. You have extra phase flip error in this case. I mean, earlier we had only bit flip error, but now we have also phase flip error. Then we looked at encoded state after single bit flip error, and error detection is a bit nuanced in this case. So you don't measure individual qubit in the computational basis, but you measure symmetries of the state. And then we looked at how the quantum circuit to measure parity, and that helps us figure out which qubit has gone through error. And then error correction was just applying the inverse of the error operator, and the logical operations on the encoded state we looked at, and finally we looked at distance of a quantum code. Okay, so for quantum 3 qubit repetition code, the x distance was 3, the z distance was 1, and that helps us figure out that 3 qubit repetition code can detect 2x errors but no z errors, and this is because for x case d is 3, so d minus 1 is 2, so 2x error, and because d is 1 for z case and 1 minus 1 is 0, so no z errors. So that's it. If you like this video, then you can, I would say, you can support us by liking, subscribing, and spreading the word around. Thanks for watching. In the next session I will try to talk about stabilizer codes and the stabilizer formalism. Thanks for watching.